This lesson's on Faraday's law. Here are the objectives. In the previous lesson, we defined the magnetic flux through a loop of wire, phi sub b, as being equal to b a cos theta, where b is the magnetic field strength, also called the flux density, a is the area enclosed by the loop of wire, and theta is the angle between the normal to the plane of the loop of wire and the magnetic field. So we saw therefore that there are a number of ways of changing the flux through a loop of wire. You can change the magnetic field strength. You can change the area of the loop of wire, for example, by making the loop smaller or making the loop bigger, or you can change the area that is within the magnetic field by pulling the loop so it comes out of the edge of the magnetic field, if that edge is within your reach. And we also saw that you can change the angle theta, the angle between the normal to the loop and the magnetic field, by rotating the loop of wire. So I'll draw another loop here. If it were within a magnetic field and I could rotate it on its axis in that field, then I'd be changing theta as well. And as we mentioned, that's what the generators that send power to our house do. Now we're going to use this concept of magnetic flux to define the EMF that is created when a flux changes. So remember, in the previous lesson, we also had bar magnets and loops of wire, and we saw that if this is north pole of bar magnet, and therefore the magnetic field is coming up out of it in this direction, then if I move the north pole of the bar magnet up like that, then I get a current induced in the wire in this direction. In order for there to be this current that I've marked in green here, there must be an EMF driving that current. And so Faraday's law is the rule that tells us what that EMF is. And Faraday's law has to do with changes in flux. Faraday's law states that when the flux through a loop of wire, remember the flux through a loop of wire is phi sub b, which is equal to ba cos theta, when that changes by an amount delta phi sub b in a time delta t, then an EMF is induced such that this is our epsilon for EMF, is equal to the negative of the change in the flux divided by the change in the time. So this is a rate of change. Again, the EMF is equal to the negative of the time rate of change of the flux. And remember, EMF is measured in volts. So this is saying that if we change the flux by more or faster, we're going to get a bigger EMF. If you want to think about it this way, if this is a graph of the flux through a loop of wire, again that's equal to ba cos theta. If this is the flux through a loop of wire as a function of time, and let's say that it was sinusoidal, and we'll see in a future lesson that it often is sinusoidal, then what this is saying is that if I were to take the slope of this graph at any point, then the negative of that slope, because of this negative sign here, would be equal to the EMF that is being generated by this changing flux at that moment in time. And it's this EMF that's driving that current, and we could work out what that current is by using our relationship that V is equal to IR, or in this case, EMF is equal to IR. Now, if we put not just one loop of wire, but many loops of wire together here into a coil, then if we have n loops of wire, we get the same EMF induced in each, and so this relationship becomes multiplied by capital N. So just multiply this by the number of loops of wire, and you get the EMF that's generated in a coil of multiple loops of wire. And that's because they're connected in series, and we know that if we connect things in series and each one of them generates an EMF, then the total EMF is just the sum of all of those. So we multiply by n the total number of loops of wire to get the EMF from all of them. This quantity n times the flux through each loop gives us the total flux through all of them. So n here is the number of loops, and phi sub b is the flux through each loop. And so the product of the two is the flux through all of them together, and that's called the flux linkage. So n times phi gets this special name that you might see called the flux linkage. All right, let's use this information to solve a problem and do some practice. Here's a textbook problem. We have a 500 loop circular wire coil, that's here, and so n is equal to 500. This is our coil of wire, and it has a radius of 4 centimeters, and it's placed between the poles of a large electromagnet. Here's our electromagnet, our 2 poles from the magnetic field. We can see this is the north pole, and this is the south pole over here. We're told that the magnetic field is uniform, and it makes an angle of 60 degrees with the plane of the coil. So here's the plane of the coil, and we're told that this angle in here is 60 degrees. Now we need to be careful because when we have theta in our phi sub b is equal to BA cos theta, remember that this angle is not the angle between the plane of the coil and the magnetic field, it's the normal to the coil and the magnetic field. So here's the normal to the coil. And if this is 60 degrees, then this is 30 degrees. So soon we're going to need this angle, and it's 30 degrees, not 60 degrees as in the question. So you need to be a bit careful of that. So getting back to the problem as stated, the magnetic field is uniform, and it makes an angle of 60 degrees with the plane of the coil. We just use that to find the angle to the normal. And we're also told that it decreases by 0.2 teslas per second. So what is that? Well, it's the time rate of change of the magnetic field. So it's delta B over delta T, how fast the magnetic field strength is changing. And we're asked for the magnitude of the induced EMF. In other words, what is the EMF? What is epsilon? We just want the magnitude. So we want the magnitude of the EMF, and that's going to be equal to the magnitude of negative n for the number of loops times delta phi over delta t. We're using the second of our two versions of the Faraday's law equation because we have n loops. We could use the first one if there was only one loop, the one without n. Now I'm going to drop my absolute value signs and drop my negative, so I get n times the change in the flux is the change in BA cos theta. So I'll make that replacement, divided by delta t. Now let's think about which of these is changing. The area of the coil in the magnetic field is not changing, neither is the angle changing. What's changing is the magnetic field strength itself. This is a bit of an unusual problem. Usually we won't see the magnetic field strength itself changing. We'll often be changing the angle. That's what happens in the generators that deliver power to our house. But if we carry on with this problem, I'm going to collect everything that's not changing off to the left. So n is not changing, A is not changing, and cos theta is not changing, but it's B that's changing. So NA cos theta delta B over delta T. But we have this in the problem. It's given to us as 0.2 teslas per second. So now we just plug in. N is 500 loops. We need to calculate our area. We're given the radius. So using pi r squared, I have pi times 0.04 meters, making sure we're working in meters, not in centimeters, squared. Cos of theta, again, we showed that theta that we need is 30 degrees, not 60 degrees, so be careful about that. And then the last part of our expression here is delta B over delta T, the time rate of change of the magnetic field strength. And that's given to us in the problem as 0.200 teslas per second. Now multiply all of those together, and I get that the magnitude of the EMF is equal to 0.435 volts. So bringing that back to the problem, we've changed the magnetic field strength and seen that that generates an EMF on this coil of wire, and it's that EMF that then drives a current around the coil of wire because it's a conducting material. In summary then, Faraday's law relates the time rate of change of the magnetic flux through a loop of wire or a coil made of multiple loops of wire and the EMF that's generated in that loop or that coil. Now you might have noticed that we effectively ignored this negative sign by finding the magnitude of the EMF in this problem. This negative sign has to do with the direction of the EMF and therefore the direction of the current that results. And that's an important consideration in its own right, and we'll look at that in more detail in the next lesson, which is on Lenz's law.